This video is on understanding and interpreting the simulated telemetry from the AMSAT CubeSatSim Lite. I'm Alan Johnson, KU2Y, AMSAT's Vice President for Educational Relations, and this is one of a series of videos showing you how to use your CubeSatSim Lite. Okay, so my CubeSatSim Lite is off right now, so I'm going to power it up. It's actually plugged in, so it's all ready to go. So I'm just going to press and release this button here, and that should power it up. Now for my ground station, I'm going to use my Raspberry Pi here. And actually, since we're going to be spending a lot of time in the ground station, I'm going to go ahead and share my screen. So hopefully you can see that clearly. And I'm going to run FoxTelem. FoxTelem is AMSAT's telemetry decoding and uploading tool that we use for our CubeSats that are on orbit. So this is the exact same tool that we use for our real CubeSats that we use for our CubeSatSim as well. So okay, so we have the CWID, the high, DE, and then the call sign. And now you can hear the FSK, frequency shift keying, data under voice, telemetry. You hear that sort of rumbling sound. And I'm going to hit start here. And there it is. We see the signal here at about looks like it's 434.903 megahertz. And I'm just gonna turn the sound off here because we don't need to listen to that the whole time. You can also listen to it in FoxTelem if you click on this monitor audio as well. Okay, so in the spectrum here, we can see the signal. This eye diagram is used for analyzing digital signals. And a good eye diagram is one where the eye is open. It's called an eye diagram because of the sort of shape here. And when it's open, you'll see a signal to noise ratio, in this case 9.8 decibels signal to noise ratio, so that's good. Now if I just force it to go somewhere else here, you'll see what a bad eye diagram looks like. There, that's what a bad eye diagram looks like. It's just random lines there. And the actual signal itself here, and that looks like a binary signal, right? It's got two levels, high and low, for a 1 and a 0. So everything looks good. Now, just to be sure, if we look down the bottom here, notice that this frames count keeps going up. And basically, it's if you see that, it's one frame about every 4 seconds or so. And that corresponds with the data rate of the data under voice. Okay, so if this is what we've got, if this is what you've got, then we're ready to go here. Now there's two telemetry modes that FoxTelem works with. One is FSK, frequency shift keying, and the other is binary phase shift keying, BPSK. So we're just going to use FSK. It's just a little easier, but we could use either of them. So this is mode 2 on your CubeSatSim Lite. So I'm going to click on the CubeSatSim FSK tab here. And it comes up into the health tab here. This is what's known as housekeeping telemetry. So it's just giving you the general status of the CubeSat, and also the status of any experiments that might be running on it. Now keep in mind that of course all this is just simulated telemetry, right? The CubeSatSim Lite, it doesn't actually have any sensors, it doesn't have solar panels, it doesn't have a battery. And so if we didn't simulate the telemetry, its telemetry would be pretty boring. But instead, the software generates some fairly realistic telemetry, and we can learn a fair bit from it here. Okay, so let's have a look here and see what we can see. So the first thing it says latest real time. So this means that the telemetry here that's getting displayed is in real time. So it's what's actually it's the latest value that's been sent from the CubeSat. Resets. So this is a count of how many times the CubeSat has actually rebooted. And if your CubeSatSim Lite is relatively new, you haven't used it much, you might have a low reset count like 1 here. But if you've used it a bunch of times, every time you power on and off or change modes or change configurations, it causes the software to restart, and that will increment this resets. Also next to it there is an uptime. So this is how many seconds since the last reboot. So since I just powered it up there, you see it's about 300 seconds. So what's that, about 5 minutes or so. I'm just going to hit reboot here, just so you can see that the resets count is going to increase. The way we reboot is we use the other button here, so the one over on this side next to the green LED that we use for changing modes, and I'm just going to press and release that button. So I'm going to do that now. Press and release. And now if I go back to the input here, you notice that the signal is gone, right? This is what FoxTelem looks like if your CubeSatSim Lite is not transmitting, or you happen to have the wrong center of frequency set here. But in about 30 seconds, this signal will reappear. So while we're waiting for that, let's take a look at the housekeeping telemetry here. So the telemetry is in different groups here: radio, computer hardware, software, battery. PSU, that stands for power supply unit. It's basically the supply for, in this case, the Raspberry Pi. Experiments, and then data on each of the 6 sides. So the axes of a CubeSat are X, Y, and Z. And the plus direction is in one direction, the minus direction is in the opposite direction. And of course, a cube has 6 sides. So that's why there's six different sets there. Okay, let's see if we are going here. Yep, so looks like we have successfully rebooted. We can see the frames count is increasing. And now if we go up here, there we go. The resets count is at 2. So again, your resets count will be different, but it's you can kind of keep tabs on how often how many times you've used your CubeSatSim Lite. Okay, so let's have a look at things under the battery box here, and it has a voltage, cell A plus B plus C, and current. So the CubeSatSim has 3 nickel metal hydride cells, and the nickel metal hydride batteries, they have a nominal voltage of about 1.2 volts per. So all 3 of them together would be 3.6 volts as its nominal, and if it's fully charged, it could have a voltage as high as 4.3 volts. And if you look here, whoops. Right there, you can see that the current voltage is 4.26 volts. So that's actually quite a high voltage, saying that the simulated batteries are fully charged. Now we can watch to see what this voltage does over time, and to see if it, for example, increases or if it decreases. And that will determine whether that can give you a clue as to whether or not the batteries on the CubeSat are charging or whether they're discharging, right? Charging when power is coming in from the solar panels, and discharging is when when there's no power coming in from the solar panels, and instead power is going from the battery to to supply the CubeSatSim itself. The other way we can tell is we can look at the current here and see the sign of it. In this case, the current is negative, minus 35 milliamps. So a negative current means conventional current is flowing into the battery, which indicates that it's being charged. And this agrees with our battery voltage here, because notice that our battery voltage has just increased, right? It's now up to 4.3 volts. Okay. So we can look at how these, you can watch them to see how they vary. You can also do graphs of these. So for instance, if I double click on this battery voltage, and I'm just going to set this for something small here. I'm setting the last values here. There we go. So I just have that set to the last 30 samples. So you can see that this graph, it's labeled with the resets, which is 2, and the uptime, going from 83 seconds to 240 seconds, and it's graphing each of these individual points here. And you can see it's happening in real time. So about every 4 seconds, it's updating, and you can see how it's increasing. Okay. So we've determined based on this that because the battery voltage is slowly rising and because the battery current is negative, that indicates that there is charging going on. So let's have a look at the computer hardware tab here. Let's have a look at the IHU temperature. IHU stands for Internal Housekeeping Unit. It's basically the term for the CPU of a CubeSat, and you can see that's 52 degrees. That's Celsius, so that's pretty warm. And if you notice, it appears to be slowly increasing. Let's have a look at what it's doing. Yeah, if you look at what it's been doing, the temperature has been increasing. And again, this agrees with if charging is going on, it means power is coming from the solar panels. And if the solar panels are getting power, that means they're illuminated. And so this indicates that the temperature of the CubeSat is currently rising. Okay, so if we look at the experiments tab here, you see the STEM payload status shows as fail, and there's no readings for temperature, pressure, altitude, etc. So right now, the CubeSatSim Lite simulated software does not simulate any experimental data there. That's why it shows up as fail. But in the future, we might write some code that actually simulates some of these, which could be interesting. But for now, there's really nothing of interest there. But let's have a look at the different simulated solar panels here. So the plus X panel, we have a look at it. It reads voltage, current, and the rotation and the acceleration. Those are actually both derived from the experimental from the STEM payload. So those are always going to read 0. But let's have a look at the voltage and the current here. So the voltage right now is reading about 1 volt, 0.95 volts, and the current is basically 0 milliamps. So let's double click on it here, and let's also look at the last 60 or so here. So this is where we are now. We're reading about 1 volt. But if we go back in time, right? If we go back about a couple of minutes here, you see that there were peaks of this voltage at about 5 volts. Now these are 5.5 volt simulated solar panels. So we would expect when it's fully illuminated to get a voltage of close to 5 volts. And also the fact that this voltage peaks and then goes down, it's expected because the CubeSats on orbit, they're not sitting still. They're always rotating. They're always spinning. And so as it spins, the one side sometimes faces the sun, sometimes faces away from the sun. So you get a peak when it's facing the sun, and you get a minimum when it's away from the sun. Now, it's a quirk of the voltage sensors on the CubeSatSim that when a solar panel is basically not illuminated, when it's off, it doesn't actually read 0 volts. It reads about 1 volt. So again, this 1 volt here. Basically, we can interpret that 1 volt as 0. So this suggests that that the solar panel is not putting out power, which kind of disagrees with what we determined before. But if we now go back and take a look here, notice that the battery voltage has dropped since last time we looked at it. And notice that the battery current is now positive, and it's pretty large. It's about 205 milliamps. So this indicates that in the time that we've been looking at this, the CubeSat, the simulated telemetry, has gone from illumination when the CubeSat is in the sun and power is coming from the solar panels to eclipse when it's basically behind the Earth and there's no illumination on the solar panels, and hence no power coming out of it. So basically, this simulated software, it will simulate an orbit, and it will switch between illumination and eclipse. So that is why we're now reading just this 1 volt. But if you take a look here, so we've just been looking at the RT column for real time, but there's also a minimum column and a maximum column. And about every 16 samples, the CubeSatSim Lite sends either a minimum packet or a maximum packet, which it keeps track of. So you can see here that the maximum value from this plus X solar panel is about 5 volts. So that's what it was peaking at when it was under illumination, and the minimum is about 0.9 of a volt. And also look at the current here. You see the current is 0 milliamps, but it was a maximum of 169. Now, one thing that can be fun here, let's see, where is it? Okay, so here is the voltage of the solar panel. So we can actually look at multiple things on the same graph. If I click on the plus here, and then I go down here and select the plus X panel current. There we go. Oh, and look at that. Suddenly the voltage across the solar panel has just increased. It's just gone up to 5 volts there. So what this tells us is that the CubeSatSim simulated telemetry has actually moved from eclipse into illumination. And if I just expand this, if I increase this last sample, so if I make this at 200, let's make it a little less than that. Like that, you can see there was this period of time here where there was no voltages or currents, but now the current is and voltages are coming again. So this period of time here is the period of eclipse when it's in darkness, and then this period here is the period of illumination. So by looking at how many seconds are between the two, we can actually calculate what the simulated orbit is. So after you've gathered some data, you can do that. You can also compare that with a real CubeSat in low Earth orbit and see whether this value is realistic or not. Some of the values that we've chosen for the simulated telemetry are accurate and reasonable values. Others we've chosen to make it so that you can see things happening faster than they normally would, so you don't have to wait a long period of time to do things. So in that sense, they're actually not realistic in terms of what you would actually get. Okay. So, we've looked at the voltages and currents for one solar panel. So we can compare those to another. So the plus Y, this is just facing a different direction. And if you look at that, it's pretty similar to what we're getting with the plus X, right? We had a maximum of 5.12, and here we have a maximum of 4.93. Maximum current of 169, maximum of 160. So that's pretty similar. And that's true of the minus X and minus Y, but if we look at the Z panel, which in general is the one facing up or down, although the axis is all relative, you see that it's actually much lower. The maximum voltage there was 1.1 volts, and the maximum current was 7 milliamps, which is a lot less. And basically, by comparing, if you assume that all these panels are basically the same size and same rating, then you can actually determine the axis of rotation based on this. So without getting into a lot of math, you can see that while the plus X and plus Y, minus X and minus Y are getting full illumination, the plus Z and minus Z are only getting very slight illumination, which indicates that the angle of the sun is quite small. Okay, so we'll just do one final thing here. I'm just going to reboot one more time here. So I'm going to go to the button here, press and release. And the reason I'm doing that is to show you that each time you reboot or each time you change your configuration, the simulated telemetry is going to be different. There will be, it might wake up in a different mode. It might wake up in eclipse instead of illumination. The ratings of the solar panels will be slightly different each time. The orbital period will be different each time. So it's kind of fun if once you've interpreted it and figured out what's going on, you can hit reboot and then come back and see what's changed since then. So let's see if we've come back up yet here. Not quite. One other thing to keep an eye on here is under this computer software, we've looked at this simulated telemetry being on. If you had a real CubeSatSim, that would say off, and it would show real values. But there's also this one called safe mode, and safe mode is something that's automatically activated by a CubeSat whenever the battery voltage is determined to be critically low. So you may, if you see the battery voltage get below a certain threshold, you may see safe mode turn on your simulation here. Okay, so looks like we've come back up here. I noticed the reset count is 3. There we go. And if you look, we've now switched into illumination mode here. We have a very large negative current there, minus 183 milliamps, indicating that that charging is taking place. Okay. So we've done all this for the FSK, frequency shift keying, data under voice mode. We could do the same thing for BPSK. The fields are almost identical, and all we need to do is put the CubeSatSim Lite into BPSK mode, which is mode 3. So hopefully you've learned something about how to interpret and decode the telemetry from the CubeSatSim